Okay. So here's an example which is kind of challenging because we write the torque equation and then you realize, oh, I need this force, oh, I need that force. Now, sorry about this, but this is supposed to be a mu, right? Okay, mu sub s. It works fine on my computer, and I don't know what's the deal with this one. But anyway, mu sub s, okay? Now, you should have a worksheet, because I actually want you to do this along with me. So grab your worksheet, and we'll do this together. I think I put this on a, this is one of my favorite problems. Hint, hint. So you better know how to do it. Okay. How far along a ladder can a 60-kilogram person climb before the ladder starts to slip? So, you know, it's going to go one of these things, right? No. Assume a frictionless wall. Great. So all the friction's down here. Yeah? The ladder's mass is 15 kilograms, the length is 8 meters, and it makes a 6-degree angle with the floor. And they give you the mu s. Okay? So, what are the equilibrium conditions? No kidding, right? Some of the forces are 0, some of the torque is 0. Okay, now hold it. Why are we even thinking about torque? You know? I mean, this is a ladder, right? But on the other hand, think about it now. You know, if the ladder changes, if the ladder slips, what happens to this angle? It changes, right? As long as you have a changing angle, you can use torque, right? So we're going to use torque as the possibility of that changing angle. All right. So what's the object? Is it the man? Is it the ladder? What's the object? Well, what are the forces acting on? The ladder, right? You know, you have a normal force. Well, we'll go over in a minute, right? But you have all sorts of forces acting on the ladder. So the ladder is the object. So what are the forces acting on the ladder? What are the forces? Okay, so we're going to use, so uppercase mg, that's going to be the weight of the guy. Lowercase mg is going to be the weight of the ladder. Okay, what else do we have? What other forces do we have acting on the ladder? Well, we have a normal force right here, right? Normal force from the wall. So we're going to have normal wall. What other normal forces do we have? Normal floor, right? Normal floor. Normal floor. And what else do we have, which is kind of crucial? What else do we have? Friction, right? Now, what's the direction of friction? If this were ice, that ladder would go this way, right? So the friction has to be this way. And, you know, we want to see how far can the guy go. So we want Fs max, right? So we have Fs max. Okay, so 1, 2, 3, 4, 5 forces. So you know the routine. Draw the force diagram, but you got to be careful where you draw everything. Okay, so there you go, right? Normal wall. This is where the painter was, mg. This is the center of mass of the ladder. You assume a uniform ladder, because what else can you assume? So it's half a L up, right? Center of mass of the ladder, the weight of the ladder. We have the normal floor. It's supposed to be F. This F is Fs max. Now look at that. I wonder why it worked there, not on the other slide. I don't know. Whatever. Okay? So this is the friction, right? Fs max. Okay. Now we're going to draw the force equation first. So I want to get rid of as many torques as I can. So where am I going to put the axis of rotation? I could put it here, right? Get rid of this guy. I can put it here. I can put it here. Oh, wow, if I put it there, I'll get rid of both of these. That seems to be the way to go. Let's put it there. All right, let's put it there. So there's the axis of rotation. Awesome. All right, now we're going to do the torque equation. So we want the sum of the torques to be 0. Okay. Let's do this one first. So here's the force line. All right. So we want the distance, the perpendicular distance between the force line and the axis of rotation. What's that going to be? Here's a force line. just going to be this, right? I think I have a picture. Yeah. Okay, so there's the force line. There's the axis, so it's this, right? It's this, which is the same thing as this. Okay, so what is this? Well, this is L. This is theta. So what's that? Just L sine theta, agree? L sine theta. Okay, but that's not enough, right? That's not enough. If we only have, if this is the only force, right? You ignore everything else. If this is the only force, it's going to be clockwise or counterclockwise. Obviously, it's going to be clockwise. So what is that? Plus or minus? It's a minus. So it's minus NW. There's the force. The lever arm is L sine theta. L sine theta. Awesome. Okay, next, let's do this. So here's the force line. Perpendicular distance from the force line to the axis is this, right? Right? Just this. Okay, here's a nice picture of it. Okay. Force line, axis. So what is it? Okay, now what are we trying to calculate? The distance up the ladder where the guy can stand without slipping, right? So we've got to call that something, so call it D. So if that's D, then what is this, right? Force line, perpendicular distance from the axis. What's that going to be? Well, it's adjacent now, right? So it's cosine. So the lever arm is D cos theta, right? There's the force line, there's the lever arm, D cos theta. But hold it. Ignore everything. Ignore the wall. Just remember that this is the axis. So if this is pulling on it, is it going to rotate counterclockwise or clockwise? Counterclockwise, right? So it's a plus. So we went plus big M, little g, d cos theta. All right? Awesome. Now let's do this one. Here's a force line. Here's the perpendicular distance, right? So let's look at the nice picture of it. Force line, lever arm. But what's this? This is just half of L, right? Because this is the center mass of the ladder. So this is, all right? So this is L over 2, adjacent, so it's cosine, right? So the lever arm is L over 2 cosine theta. And ignore the wall, ignore everything except for this and this. How does it make the ladder rotate? Counterclockwise, right? So it's plus. So it's plus little mg times L over 2 cos theta. L over 2 cos theta. And how did I get that one? Oh, yeah. And that's it, right? Yeah. Oop, you didn't see that? All right. And since this is the axis, this has no lever arm, this has no lever arm, so we're done. Woohoo! Now, what's the problem? What's the problem? Problem is, I know L, I know angle, I know the M's. I'm trying to find D, right? But what don't I know? I don't know NW. Rats, right? So I don't know NW. So see what I mean? This is one of these problems where, you know, you got to do more than just the torque. Bummer. Okay, that's okay. NW is in the x direction. What do I want to be true about the sum of the forces in the x direction? Sum is 0, right? Okay, no problem. We can do that. So we want to get NW, right? So the sum of the x forces, NW to the right, and what else? Fs max to the left. So NW to the right minus Fs max, and that equals 0. So therefore, NW equals Fs max. But what's Fs max? Mu s n floor, right? Mu s n floor. Do I know n floor? No. Okay, so I got to get n floor. Oh, man. No problem. Okay, so now I got to get n floor. So how am I going to do that? With the sum of the y's. Okay, sum of the y forces. So what are the y forces? I get this one going down, I get this one going down. So I have m plus little m g going down, and then I have normal floor going up, and that equals 0. So therefore, the normal floor equals m, that's like an m plus mg. Now, no kidding. I mean, right? Didn't we kind of expect that, you know? I mean, it's the total weight, right? The mass of the guy, the weight of the guy and the weight of the ladder. So this is no big surprise, right? Okay. All right, so I got it. Okay, so now I got to just, oh my gosh. Okay, so now I got to fill in the blanks without not a whole lot of room. Okay, so NW is mu s NF, and that's that. Okay, so I got to write that down. Oh, golly. Okay, so NW is, minus. So I have a minus, all right, so I have a minus mu s times n floor, and n floor is that. Here, okay? All right, awesome. Okay, let me make sure I didn't goof up. Yep, great, okay. All right, now we just got to solve for D. Solve for D. Okay, let's wait a second. Let's see if we can sign. Let's see. Okay, let's try to simplify it. Let's divide everything by cosine. That'll make it easier, you know. So that goes away. That goes away. Sine over cosine is tangent. That makes it nicer. Might as well keep it simple, you know. Okay, now we're going to solve for D. So we're going to put that on the other side and that on the other side. So we're going to have m, wait a second, and let's get rid of the g too. Let's get rid of the g. Get one there, one there, one there. And you better be careful with the m's. That's a big M, that's a little m, right? Okay, so we're going to put this on the right, this on the right. So we'll have, well, let's just divide, whatever. So we have m d, this thing, equals mu s m plus m L tan theta, and then minus that, minus ml over 2. All right, now we're going to divide by uppercase M, uppercase M, okay, all right. And let's see if I believe myself. Yep, I sure do. All right, awesome. Okay, now look at, this is a D, correct? It's a D, right? Look at the units. So kilograms, kilograms, we're just going to have a length. Here we have kilograms, kilograms, nothing, length. So the units are good. So you plug everything in. I promise you, you get 6.8 meters. Okay, so you better know how to do that. It's very important because it's, it's kind of like a nice final exam question, because it uses forces and it uses torques. It just uses a lot of nice concepts. Force diagram, torque diagram, I mean, great problem. Make sure you know how to do it. Okay, so we've been working on, rotational versions of kinetic energy, rotational version of force, but what else haven't we done yet? We don't have a rotational version of F equals ma. So let's do that, all right? Let's get our rotational version of F equals ma. it's the most important equation in all of classical physics. We should have done that earlier. Well, we couldn't. That's all right. I guess we could. I don't know. All right. Let's just do it the lazy way. What do you say? F equals ma. This lazy way doesn't work all the time, by the way, but it does now. What's the rotational version of force? Torque. What's the rotational version of m? I, right? Rotational inertia. What's the rotational version of A? Alpha. Ta-da! Done. Right? So that's, honestly, that's the rotational version of Newton's second law. Torque equals I alpha. And I think that's the easiest way to do it, right? That's what I mean. If you know this, and if you know what these things stand for, bingo, you get it for free, you know? You just do it. Okay? All right. Let's kind of talk about this some more. So m, mass, is the measure of inertia. We've said that many times. And what's inertia? Inertia is the natural tendency of an object to remain at rest or at a constant velocity. So if it has a small inertia, it's easy to change the velocity, right? There's a large inertia, it's very difficult to change its velocity. Okay, now we're talking, okay, I is the measure of rotational inertia. Rotational inertia is the natural tendency of an object to remain at rest or at a constant angular velocity. That's the thing, angular velocity. Okay, so F equals ma, a force causes a linear acceleration. Torque equals I alpha. A torque causes an angular acceleration. I mean, it all makes sense, right? It all makes sense. If you understand the linear physics, you understand the rotational physics. Just different words, you know, torque, rotational inertia, stuff like that. But I mean, it's all related, you know. It's all wonderful. All right, so that's that. Now, we haven't talked about rolling motion yet. We need to do that. Rolling motion. Oh, sorry, jumped ahead. Sorry. Okay, torque equals I alpha, where I is that crazy mr squared thing. So look at this equation. If the mass is located at large r, I will be large or small? Well, from the equation, large, right? Large. Therefore, since torque equals I alpha, if you have a large I, what kind of torque are you going to need to change the angular velocity? A large torque, right? Kind of makes sense, right? Okay, just like if a large mass, you need a large force to accelerate it, okay? See all these nice analogies? All right, great. Let's talk about rolling motion. No slipping. So, what's rolling motion? Can you see it on the floor? Hold on. Can you see the floor? So this is rolling motion, okay? And there's no slipping. This would be slipping, right? We don't want that. We just want rolling motion. Thanks. Okay, so that's what we want to talk about, rolling motion. So we got the pioneers, right, when they're rolling those wagons across the plains. Okay, that's what we want to talk about. All right. So rolling motion is really, well, you'll see. Okay, so this is called translational motion, right? Just something's moving from point A to point B, right? You know, this is what we studied a long time ago, just translational motion. Okay? This is just, so I call this pure translational motion, right? There's no rotation, it's just translational motion. On the other hand, this is pure rotational motion, right? The wheel's not moving anywhere, it's just rotating. This is pure translational motion. Okay, so what is rolling motion? Well, the wheel is moving, so I have translational motion, but it's also rotating, so I have rotational motion. So rolling motion is both, right? It's translational motion and it's rotational motion. All right, that's what's cool about it, okay? So the wheel moves, the wheel spins, you put them together, just think of this as an equation, right? So pure translation plus pure rotation equals rolling. I mean, that's what it is. I mean, if you think of it that way, it's going to help you understand this really, really well. All right? So we're actually thinking of it like an equation, you know? Pure translation plus pure rotation equals rolling. You can see here that every point is moving to the right, right? V equals r omega. Here, you know, this point moves this way, this point moves that way, this point moves that way, this point moves that way, right? Omega is like this. Then you put them all together and you get this rolling thing. Okay, so let's talk about it. Okay, first question. What is the velocity here? And I'm going to be really specify. Remember, whenever I say velocity, I mean instantaneous velocity. What is the instantaneous velocity? Right there. Just use the equation, right? Use this equation. What is it? So pause your video and figure it out. Remember, we have rolling without any slipping. Okay, well, what is it? It's 0. What do you mean 0? Well, come on. This piece here is moving that way. This piece here is moving that way. So we get this plus this. What do you get? You get 0. 0? Yeah. We don't want slipping. I mean, think about it. When you walk, what's the instantaneous velocity of your foot or your shoe or something like that? It's 0. If it were not 0, what do? You'd fly. You know, you'd slip or something like that, right? You wouldn't, right? You'd slip. So that's what it means with no slipping. Velocity is 0. Velocity is 0. You don't believe me? Well, look. So here's a bicycle wheel that's rolling. You notice how you can see the spokes here? Right? Because its instantaneous velocity is 0. Here's a better picture. Look at that. I mean, this person is pedaling the bike. But what do you notice at the bottom? The instantaneous velocity is 0. Okay? Interesting, huh? All right, now, tell me what the instantaneous velocity is right here. So pause your video and figure it out, please. Well, I hope you say 2v, because this has a v pointed that way. This has a v pointed that way. So v plus v equals 2v, right? 2v. 2v, or 2r omega, whatever here, you know, right? Because this is r omega, this is r omega, so you get 2r omega. Twice. Now you say, yeah, sure. Look. What do you notice at the top? See any spokes? No. Why not? Because they're going really, really fast. 2v, you know, or 2r omega, whatever you want to call it. See any spokes there? Just barely. But it's going really fast there, okay? It's going really fast there. What do you know? Okay? Now, how is this v connected to this v? It's pretty obvious they're the same, right? They're the same. Okay? They're the same. All right. So, what is the kinetic energy of a rolling object? Well, use the equation. We have the kinetic energy of a pure translation, kinetic energy of pure rotation, that equals this. So we have two terms, right? We have two terms. So for rolling motion, the total kinetic energy is k translational plus k rotational. 1/2 mv squared plus 1/2 I omega squared. Two terms, right? Translation plus rotation. Oh, finally a question for you. Two objects having different masses are at the top of a frictionless ramp. The objects slide down the ramp, frictionless. Which object will have the largest final speed? Now you should know this, just like that. If you don't, you know, think about it. There's no friction, so mechanical energy is conserved. So just use mechanical energy conservation. All right? Okay, so pause your video and figure it out. Okay, hopefully you have it. Let's do mechanical energy conservation. So at the top of the ramp, so we have mgh equals, and then all right, so at the top, there's just potential energy. At the bottom, there's just kinetic energy, 1/2 mv squared. What do you notice? Masses cancel, right? So the speeds are the same. The speed just depends on the height. Remember we learned that a long time ago, right? So the velocity is just 2gh square root of. Doesn't depend on mass. Doesn't depend on mass. Oh, wow, I even showed it to you. Oh, nice guy. Okay, wow, guess what? With rolling motion, oh my goodness, completely different. Completely different. All right, here I is very, very relevant. It doesn't just cancel. So now we're going to do a little demonstration. Just to show you that the I, you can't just ignore it like you can the mass. All right, hope it works. Okay, let's see. Hoop versus disc. Hold on just a second. Okay, good. All right, so we're going to concentrate on this. We're going to have a hoop versus a disc and see which one wins. So, stop. Hope they don't smash into each other. All right, so hoop versus disc. Ready, go. Okay, the disc. All right, let's do different sizes. All right, hoop versus disc. Ready? Okay, let's do, let's really try to mix it up here. Okay, so we had hoop versus disc. All right, which one always wins? I mean, let's see, what else can I do? Oh, let's do this one. Okay, so the disc always wins, right? I mean, I kept changing the sizes and everything, but the disc always won. True? Always won. Okay, now what I want to do, okay? Now, disc always wins. Explain it. Look at these look at the formulas up there. Which one has the largest eye? The hoop has the largest eye. So therefore, it's more difficult to get the hoop rotating than it is the disc, right? So therefore, doesn't it make sense that the disc is always going to win? Yeah, because it has the lowest eye. All right? So that makes good sense, right? Okay, let's see. Let's do sphere. Let's do some spheres. So now we're going to do okay, so remember, this one had the lowest I, right? Because I disc is 1/2 mr squared. I hoop is mr squared. So it seems that the lowest I is going to win. It makes sense because the lowest I, right, means it's easy to get it rotating. All right, so now let's do the sphere versus the hoop versus the disc. So now you predict, okay? So pause your video and make a prediction. Which is going to win, which is going to come in second, which is going to come in last. Okay, so we're going to predict that the one with the smallest I is going to win, right? Which is the smallest I? The sphere. So this is going to come in number 1. What's going to come in number 2? The disc, number 2. And the hoop is going to be last. But we'll say number 3. That doesn't feel so bad. All right, so let's do it. So sphere and hoop. Okay, so the sphere kills the hoop. Well, we expected that. Now let's get sphere and a disc. Oh, that was closer. Woo, that was closer, huh? But which one won, though? The sphere. Okay, let's do a small sphere. Let's do a small sphere and a hoop. Okay, let's do a small sphere and a big disc, or I don't know, whatever. Sphere and a small disc. Do I have a small disc? Not really. Let's do this one. Okay, so what do you notice? Sphere always wins. Disc always comes in second. Hoop always comes in third. Always. Okay? It doesn't matter, you know, the size, the mass, or anything like that. It just depends on the what? It depends on the rotational inertia. That's all it depends on. Rotational inertia. Well, you know, we should be able to prove that, right? Using the laws of physics, we should be able to prove that. So that's what we're going to do. We're going to prove it. And you're going to do this in lab. And you might even see this on one of the exams. Maybe even the final. I don't know. But this is kind of important because it uses lots of concepts that we've had throughout the entire semester. So let's do it. It's going to take a while. Let's quit. We'll do it after.